So here's an example from statics. Okay. This example says, using force distance method, determine the moment about A due to the force exerted on the beam at B by the cable. Let M is equal to 70 kilograms. Okay. So essentially in order for us to find the moment about A due to the cable force at B, we first need to solve for the cable force at B. Okay. The cable force at B would be this force here, highlighted yellow. Okay. So essentially this problem is a combination problem of static equilibrium and then moment about a point. Okay. So once again, the first thing we'll do is we'll do a free body diagram of the mass M. Okay, so the weight of this mass is going to be mass times gravity, which is 70 times 9.81. Okay, and then the units are in newtons since we are working with metric units. Okay, so essentially I'm going to label this point C and point D. Okay, so point C is this point here. We'll go ahead and show the tension TCD, and then we'll show the angle, and then we'll show this tension TCB, and once again we'll show the angle. Okay, we will use the XY Cartesian coordinate system, and then essentially we'll apply our equations of equilibrium. In this case, the equations of equilibrium, this is a 2D equilibrium problem. Okay, so essentially we'll start by using sum of forces in the X is equal to 0. Okay, and essentially it'll be TCD positive cosine of 45 minus TCB cosine of 30. Okay, so essentially when our reference angle is relative to the horizontal axis, we use cosine, okay, to get the X component. Okay, and then the directions, TCD is positive. The X component of TCD is positive based on the direction that we see here. It would be going this way, right? The component of the force, the X component of that force. Whereas for TCB, it would have a negative X component, okay? Because the X component of TCB goes this way. Whereas once again, for TCD, the X component goes this way, okay? How do I know that's my convention? Essentially is based off of this Cartesian coordinate system, okay? So essentially here, since we have two equations, two unknowns, we will write, let's say, TCD in terms of TCB. So we'll have cosine 30 over cosine 45, which essentially we'll get, we put it in our calculator and put these values. And essentially we get 1.224. Okay. So once again, from the summation force X is equal to 0 equation, we get TCD in terms of TCB. So now we'll do sum of forces in the Y is equal to 0. And essentially we'll get a positive TCD sine of 45 plus TCB sine of 30, okay? Both have a positive y component, okay? You look at essentially you look at the free body diagram that we drew, and you see that TCB has a positive y component, whereas TCB also has a positive y component, okay? The weight force has a negative y component, and that's where it comes into play right here. We set it equal to 0, okay? And now what we'll do is we will substitute TCD in terms of TCB into our sum of force y equation. So TCB 1.224 sine of 45 plus TCB sine of 30 minus 70 times 9.81 equal to 0. And essentially, we crank this out in our calculator. And we get TCB 1.365 equal to 70 times 9.81. Solve for TCB. We get 503.0 newtons. Okay. So essentially that is the force in question. TCB is the force essentially at B. Okay. So from this step, we could essentially draw a picture of the beam AB. This is A, this is B, okay? And then as a student, you might ask yourself, well, what direction am I putting the force in? Okay, at B, obviously. So I'll show it like this. Okay, so essentially we gotta think about Newton's third law of motion, which says equal opposite forces. So when we move from one free body diagram to the other free body diagram, okay, the forces shared between the free body diagrams have to be equal and opposite. That's what that means. Newton's third law, equal opposite forces. So that's exactly what we do here. And then this would be the force TCB, okay? The direction is still the same, relative obviously to the x-axis. That is the 30 degrees that you see here, okay? So that's pretty much what we have in terms of the force at B. So I'll go ahead and shift this diagram up so it doesn't interfere with our work. Essentially, that's the type of neatness that you'll see in a tutoring session with me. So now we will show you the distance from A to B. And essentially that'll be 3 meters. Okay. And then I'll show it like this. I'll put it like this, okay? So whenever we do force distance method, I always recommend that my students break the force up in components. Okay, so this is what I mean by that. So I'll go ahead and draw another diagram just to keep things as neat as possible. Okay. So essentially here, I'll go ahead and erase this. Okay. And then we'll go ahead and break the force up in components. Okay. So the x component of TCB essentially is TCB cosine 30. Okay. And then the y component of the force is TCB sine 30. Okay. So essentially this allows us to see the forces. It allows us to see which component of the force is going to create a moment about a point, okay? So essentially the convention that we use for moments, if a force creates a counterclockwise rotation about a point, then that moment is positive. If it creates a clockwise rotation, the moment is negative, okay? So we have two components of, so we have the two components here, the X and the Y, okay? If we look at the X component, the line of action of the X component of the force, I'm using it highlighted yellow, that's the line of action, okay? If the line of action intersects the point of interest, in this case A, then that means there is no component, okay? There is no component. That X component force is not creating a rotation, right? It's essentially pulling the beam rather than rotating the beam, okay? That's how a student should visualize moments, okay? A moment is essentially the tendency of a force to create a rotation about that point, okay? The point of interest. Like I said, the X component, TCB cosine 30, is pulling the beam rather than making it rotate or wanting to make it rotate, okay? Whereas if you look at the vertical component of the force, right? If I use, let's say, light gray, and I use this color to show the line of action of the force, right? The line of action of the force is not intersecting A, okay? And we could see that it wants to create a rotation about A, okay? Therefore, it creates a moment, okay? So essentially, the moment about A, force distance method, is going to want to create a clockwise rotation, right? Just picture it like this. Picture AB being a stick, okay? You're holding point A with your fingers and you're pulling down at the edge of the stick, okay? What does the stick want to do? It wants to rotate clockwise, okay? And essentially that's how you want to visualize it, okay? Always visualize it conceptually, right? Always think about it from a real world application, okay? When I do a tutoring session, that is what I aim to do. I want to apply these concepts to real life scenarios because essentially that's what engineering is, okay? So essentially moment is going to be negative due to rotation. A lot of times students look at the direction of force and they immediately assume that the moment is negative because the force is going down. That's not the case. A moment is not a force. Like I said, a moment is essentially the tendency for a force to create a rotation. And the sign convention for a moment is based on the direction of rotation. If it's clockwise, it's negative. If it's counterclockwise, it's positive. So essentially we have negative TCB, okay, sine of 30 times the perpendicular distance. In this case, the perpendicular distance of the line of action of the force to the point of interest is 3 meters. Remember, the units of force is Newton. The units here is meters. The overall units of moment is force times length. So in this case, it's Newton meter because our newtons is the force and our length is meters. Okay, so we got 503 sine of 30 times 3. So plug this in our calculator. So we get minus 754.5 Newton meters. Okay, if you're in an engineering class, many times professors ask you to use 3 significant figures, so it would be 755 Newton meter. And essentially that is your answer.